All right, one last example problem involving centripetal acceleration. So a conical pendulum formed by attaching a 500-gram ball to a 1-meter long string. It moves in a horizontal circle that has a radius of 20 centimeters. So 20 centimeters is the radius of this circle it moves in. Now, horizontal circle means this circle that's traced out in the picture is the same height from the floor at all moments in time. The picture they've given us is kind of down at an angle to get a picture of what's happening. The ball is tracing out a cone. So the ball itself traces out a cone. The circle, the string traces out a cone. If I were to look at this ball perfectly from the side, I would just see the edge of the circle. The radius would be there. The string would go up to here. So the string is held in place at the top. The point of support is what it's labeled in the original picture. The string has a length of 1 meter. The radius it makes is 20 centimeters, so 0.2 meters. We know there's an acceleration that points towards the center of the circle. So depending upon where the ball is, towards the center of the circle is varying. My picture, this side view, I'm choosing the moment in time when the ball is at the far right in my view. At that moment in time, I know the tension points up and to the left towards the point of support. I know the force of gravity points straight downwards. The acceleration, the centripetal acceleration, points to the left at this moment. So this tension force has an X component and a Y component. When we think about the net force needing to equal MA, in the radial direction specifically, it's the X component of tension that points to the left. So that has to be what is creating the centripetal acceleration. So the X component of tension needs to equal mass times the centripetal acceleration. The Y direction, up and down, well, the problem tells us that the mass is moving in a horizontal circle, meaning it's not moving up or down. So that Y component of tension is balancing out gravity perfectly. There's no acceleration in that vertical direction. Now we do have M, we do have G. We're looking for tension in the string, the ball's angular speed. So to talk about tension having X and Y components, we need an angle of some sort. So if I call the angle with the horizontal theta, I know the angle that tension makes with the horizontal is the same as the angle the string makes with the horizontal, because the tension vector is directed along the length of the string. I have enough information in here to figure out what this angle is, and it's not sine. I know the adjacent side is 0.2. I know the hypotenuse. So the cosine of theta will be 0.2 over 1. So inverse cosine gives me an angle of 78.46 degrees. So I know this angle in here. The x component then of the tension is going to be t cosine of this angle. The y component will be t sine of this angle. Now, in terms of centripetal acceleration, we can substitute in either v squared over r or r omega squared. In terms of choosing, I'm going to look at what I'm being asked for. Since the problem is asking for angular speed, I'm going to plug in the r omega squared. All right, so let's see. We know mass, we know g, so actually we can solve our y equation now for tension. I'm going to bring it over to the left side. T sine of our angle is going to equal the mass, which we do want in kilograms, times g, so that our tension will be in newtons. I'm getting 5.001. So 5 newtons is the tension. This is our answer for part A. That tension, of course, is the same as the T in the radial equation. So I can put in my 5 newtons times the cosine of that angle. That's the x component of the force, of the tension specifically. The mass we have, r, the radius of the circle the mass moves through, 0.2, so in meters. So I can solve for omega here. I'm getting an omega 3.163, and the units on this will be radians per second. We're going to technically come up, if we looked at all of our units as we walked through, we would come up with 1 over seconds. The radians are implied. The problem, though, is asking for this angular speed in revolutions per minute. That's what RPM stands for. So we need to do some unit conversion. We know there's 2 pi radians in a revolution, and there's 60 seconds in a minute. So the seconds will cancel, the radians cancel. I'm getting 30. I have at best 2 sig figs, so I'll leave it at that. Revolutions per minute. So the approach, very similar to what we've been doing this whole section. This new part is the centripetal acceleration. So remembering whenever there is a change in direction, the object is going through some sort of circular path, we need to account for the centripetal acceleration pointing towards the center of the circle.